Good morning, everyone. So I'd be giving a presentation on BGP routing table report. This is a report from a period between January 2006 to end of 2016. Here we analyzed top ASNs which are well connected across the world. We analyzed how the growth has been with respect to the interconnection of those ASNs, things like growth of prefixes, not much into deaggregation, mostly around how the prefixes have grew over this time, and changes across the multi-homing. How many networks were multi-home with one provider or two providers, say in 2016, and how it has been now. So overall mapping of that data. So I'll start with the ranking of top connected networks, and before I jump into the data, I would like to inform that it's tricky to find who peers with whom. So this data is supposed to be as good as we see from the various route collectors. If some data is missing out in route collector, so for instance, if someone is peering with someone else and that data is not visible outside to the world, then that data won't be reflected in the in this chart. So here's how the networks used to look like back in 2006. Let me see if I can use the pointer. So here on the top we have the AS number and then the number of adjacencies we see in case of IPv4 world. So back in 2006, AS701 was on top in the list in terms of adjacencies. AS701 is Verizon, then it was AS7018, AT&T, followed by AS1239, Sprint, AS174 Cogent, and AS3356 level 3. So this is what we see from multiple route collectors during this period, and we collected data for entire year multiple times in a month, while here what we are presenting is data which is for December only. So just for the sake of presentation, it's for December. We have the raw data for remaining years, multiple times of month in every year. So they stayed pretty much stable for a while. From 2006 all the way to 2016, 701 was on top. There were changes around in 3356 during this time. So you can see 3356 jumping onto the 4th rank, and then all of a sudden to the 1st rank with this time. And the difference has been reasonable here. They had somewhere around 2,600 adjacencies, and it is quite possible to view the adjacencies of these networks because these are IP transit providers. Since these are providers, a lot of people have the full routing table from these providers and they dump them into various route collectors like Oregon Route Views or RIS, etc. Up in 2010, we see Cogent AS174 coming up on the top, followed by level 3, AS3356, and then AT&T, and so on. Here also AS6939, the company I work for, Hurricane Electric, we appear somewhere on the 5th rank with 1,500 adjacencies. This continues for a while. I'll jump on to the next one. Okay. So in 2012, we see Cogent staying on top all the way up to 2015. The situation was more or less stable for the top 4 of them. There were changes around in the 5th rank with Verizon coming up for a while, AS4323 for some other time. I believe that was TW Telecom, if I'm not mistaken. And then in 2016. Hurricane Electric came on the 1st rank with somewhere around 6,000 adjacencies, followed by Cogent with around 5,000 adjacencies, and so on. This was the case of IPv4 world. I'll proceed with the changes in peering by plotting them. So here you can see how this went on. So for instance, this is AS174 with a reasonably steady growth. Here we see the graph of AS6939. Here's the graph of level 3, AS3356. So you can see some networks had a growth earlier and then went down. Some are slowly going down in terms of their adjacencies, maybe because they are depeering or maybe they are not getting more customers, somewhere like that. And here adjacencies mean peers as well as downstreams. We are not differentiating between peers and downstream because it's technically extremely hard to do that at a larger scale when you're mapping the entire visible ASN space. And all the ASNs which are appearing here are the ones which actually announce the routes. There can be a number of other ASNs, we did not rank them, which are just allocated by RIRs and never announced any route. Here's the case of IPv6, and since IPv6 was extremely new during his time, you'll see the top ranks were just somewhere 144, some even less than 200 for most of the time. So AS3257, which was Tynet, I believe that's GTT now, that used to be on top in 2006, followed by 2914 NTT, and then some other ASNs. And since IPv6 peering was extremely low, a lot of ASNs appeared and disappeared during this period as they went on peering with more and more people. So AS3257 was still up on the rank 1 in 2007, followed by NTT. Here we got Hurricane Electric's ASN on the rank 3, followed by 30071 and 6175. After this, for most part, HE got here on the rank 1, which, as you know, we're pushing for lots more IPv6, followed by Tynet, NTT, and here we see the appearance of Global Crossing, which is now level 3. It was there for a while in the routing table as the one of the most connected networks in V6, and so on. So, in case of V6, I would say before 2010, there was a lot more changes around because the numbers are extremely low. So anyone doing more than 70, 80 peerings was appearing in the list over here. After 2012, we see a reasonable stability with more and more larger providers, as one may expect them in the list. So HE followed by Cogent, followed by level 3, then AS1 3030, and the Tynet, the GTT, which is now GTT, I believe. So that has been the ranking as per December 2016 in case of IPv6 address space. And as I said, we did not differentiate it in customers versus peers. So you may see a network like HE with lots of customers and lots of peers. You may also see other networks in the list which may be having reasonable amount of peers with the other larger ones, while lots and lots of downstream. And here we also see appearance of Tynet in 2014 and 2016 in the top list. Here's the plot of how the adjacencies change has been. This is the graph for HE's network. Here's the graph for Cogent AS174. This is for level 3, and for remaining you can see a lot more interesting patterns. So for instance, AS37100 wasn't really doing V6 for a while and suddenly jumped in 2013 in the December of 2013. And in case of Tynet, there has been usually linear growth, I would say. Here's the year-on-year changes in the ASN. And again, as I said, this is about the ASNs which are visible in the table. We literally dump the routing table from collectors and pick the ASNs up. So any ASN which has been allocated but not being announced is just not on the list. Any ASN, even if it's announcing V4 only or V6 only, is in the respective data set. So in January 2006, there were 21,000 ASNs which were visible in the global table, while after 11 years, in the end of 2016, there were 56,000. On an average, it's a growth of 14.76% every year for this 11-year period. And if we plot it, I personally thought there might be some interesting changes in the pattern, especially around the fact that a lot of cloud providers as well as CDN providers came up during this period. But we don't see a lot happening in the ASN space because of that. Maybe a lot of them are using other networks, IP space, and other networks ASN. So the change is not that drastic as it should be. One may expect in these graphs. In case of new ASNs getting online, so these are the chart for the new ASNs which appeared during this period. For most part, it's within this number. There is not much change. Somewhere around 300 ASNs appeared almost every year during this time. Going further for IPv6, there has been a huge change since IPv6 came up somewhere around this time, especially with the ISOC launch and other major events. So in 2006, only 590 ASNs were announcing V6 addresses, and by end of 2016, there were around 12,000. Year on year, that's somewhere around 186% change, but that may overall go down over time as more and more people have dual stack their routers. Although I think this is purely reflecting who is announcing V6. It's not reflecting who is allocating V6 addresses as well. That makes a big difference, because I know personally lots and lots of networks which announce address space while still not have configured their end devices and are not allocating V6 all the way up to the end. So the picture is not as good, maybe, if we talk of V6 up to the end deployments. We can clearly see the ISOC launch day here. So ISOC launch day, we see a clear jump here. In case of World IPv6 day, there was a major jump when people turned on V6 for testing, and after that, for the launch date, also we see a jump in the graph in the V6 announcements, and it has been reasonably okay after that. We could not figure out this spike over here. We could not relate it to any specific event. It was probably more of a noise during this period. Maybe someone announced a lot more routes and something like that. I'd be interested to hear if anyone has an idea. Here's a quick info on the growth of IPv4 prefixes. So the prefix growth has been reasonable. There was somewhere around 200,000 routes during that time. Now it's slightly above 600,000. I believe it's somewhere 650,000 at this period now when we are presenting this data. And growth has been quite high, since lots and lots of address space has depleted, and people are deaggregating a lot more prefixes. So lots and lots of /24s are visible these days in case of IPv4 table. In case of V6, as one may expect, after 2012 there has been a reasonable jump, and I would like to say in both of these cases we are putting up any prefix announcement which is above /24 in size. So anything /24, /23, 22 is visible in this data. If it's /25 or 26, which are visible on the route collectors, we have just avoided putting that kind of data. In case of V6, we picked the boundary which everyone expects, the /48 boundary. So any announcement smaller than /48, that is /49, 50, is being ignored. There are lots and lots of /64s, /126, and /128s visible if you look at the Oregon route views data. They are collecting that data, and that's a good thing to collect, while lots of people are still leaking those routes out of their router. So we have not included that in this chart, because that would just degrade the whole values. It won't make any sense. A lot of people anyway are filtering that out in the production network. Comparison of IPv4 and IPv6. So how many ASNs still need to do V6? This chart tells us that. Here is the number of ASNs which are announcing V6. Again, this is purely on the edge side. They're announcing, it's visible, it's there. Not on the allocation side, whether they are actually deployed V6 all the way up to the end users. While in case of IPv6 is huge, so ideally we want this graph to at least overlap, if not exceed the V4 graph for better internet. On the right side, here's a graph which we never want to see overlapping. This is the announcement of address space in IPv4 world, and this is the address announcement in IPv6 world. I really hope it stays small, considering the fact that IPv6 is very high in density. So each /48 announcement is really huge, which is the least announcement which we picked up in this chart. Anyone announcing /32, or even some extremely large operators announcing /25, /29s, that's huge in V6 space. So we do not really expect them to be announcing more and more address space as they grow, since that covers a reasonable chunk of users. They can allocate a lot of addresses out of that allocation and out of that announcement. Next is the growth of multi-homing. So we tried to look how many networks were multi-homed earlier with, say, one provider all the way up to 5 providers, and how many are multi-homed now, to find if there has been a change in terms of multi-homing. We were very interested to see if more networks are now relying on multiple networks or lesser networks. So here's the data, and again, we collected data for multiple times in every month, but for the sake of presentation, we are presenting only December's data for each year. So you can see in case of December 2006, there were 8,000. So this is the total visible ASNs were 24,000, out of which 8,000 were having just one adjacency. And this could be a peer, this could be a transit. Ideally, for one, we can assume it would be transit, because the ASN would be connected to internet somehow. So, so a lot of these were purely single-homed, extremely likely transit pair. If not transit, then it would be an interesting scenario why they were with just one pair. With two pairs, it could be multiple transit, it could be a picture of one transit and a mix of one pairing. So this is how it went on. All the way in December 2016, we see out of 56,000 ASNs, 21,000, so little less than half of that was still single-homed, single ASN connected network. With 19,000 connected to two peers, and it so goes on. Beyond this scale, the number of networks connected to more than 5 peers is extremely low. We plotted this out to see if it makes sense to find the change. So this one shows the total number of visible ASNs, the growth over time, as we saw in the earlier chart. This one shows the networks with one peer versus two peers. So it's kind of interesting. There were more networks with two peerings earlier. As you can see on the graph over here, it says two peers, and there were slightly more networks. And somewhere in 2012, this overlapped. So now there are lesser networks with multiple peers. There are more networks with just single peer over this period. In terms of other 3, 4, and 5 and more peers, the number of networks is extremely low beyond this point, and we could not see any major change or any graph cutting others. So there's no pattern change, and it has been pretty much similar. But this part was interesting. More networks are relying on a single provider these days over time, as they were relying in, say, 2006. I picked up the data for adjacencies in Middle East since I was presenting data over here. An important thing here is that I did not pick up the ranking of the ASN, since the number of adjacencies is considerably low. So if we try to rank them up, it becomes harder. It's easier to rank networks which are up on say top 5, top 10, or even top 100, since the number of adjacencies is unique. If you go beyond that point, number of network with say adjacencies 10 or 20 or 30, it's lots and lots of them. So how can one rank them? Should one rank them all together? And plus the rank won't really make sense at that scale. What we tried to put was to see putting the adjacencies, the number of adjacencies networks over here have. So here we see the local host with Omantel. We could see from the public collector data, the number of adjacencies were 4 back in 2006. It kept on increasing, and in 2011 it was 12. I'll come on this data. There's an important understanding of this data once I present this chart. For the Ooredoo, the other provider, we could not see the route announcement up to 2009. Someone may correct me if the ASN has changed over this time, but probably the ASN wasn't visible. Maybe they started operation back here, or they were not using this ASN up to this point. So they were not visible, and they came up online in 2010. For Etisalat AS8966, this is how has been the growth of adjacencies. For DU, the other larger provider in Dubai, so 4, 7, and so on, the adjacencies has increased. Here's for STC, followed by ITC. I'll come on the more latest data. Here, for 2012, it has been 16, 20, and so on. So now in 2016, we see somewhere around 59 adjacencies for Omantel. And it's important to understand this is not completely correct. We know for sure, based on our conversations, the number of adjacencies is slightly higher than this number. There are slightly more adjacencies. The reason it's not reflecting it in this data is because a lot of adjacencies happen to be just the network peers, not the downstream. Because they are peers, routes are kept local within the region. So Omantel might be peering or might be connected to some other regional provider, learning their routes and announcing their routes. Both providers are exchanging routes while no one is announcing to upstream, which is a perfectly fine situation. Since none of them or their downstream, which has the full table, is putting those routes in a public collector, outside we just have no idea who they are connected to. And you might see this kind of problem with our tool bgp.he.net, as well as you might see similar thing with the stat.ripe.net, that a lot of times adjacencies are not visible as you may expect. And this is true for larger content players as well. Companies like, say, Google, Facebook, a lot of their peerings won't be visible in these tools because neither of the side is dumping the routing table data in any of the route collectors. So it's just not possible to know who one is connected to. So as I was saying, if you don't see your ASNs data being reflected correctly here, it's extremely easy to get it corrected. Here's how you can get on the list in the top: follow and promote open peering policy. It makes sense to have open peering policy and interconnect with anyone else. At Hurricane, we follow open peering policy. We connect with anyone who likes to peer with us. Peer at internet exchange points. This is the last point I would like to stress on over here is these are the public route collectors. Try to share your routing table to one of these public route collectors. So from outside, there is a visibility on your peerings, who you are peering with, and one can have an understanding of that. It would be also good to host things like RIPE atlas probes, so one can trigger trace routes from your network and figure out how's the connectivity like. Start an IXP in your region if it's not there already, and use peering DB list yourself so that others can find you and interconnect. Some of the quick conclusions: peering is good, and this is one of the cool quotes I like to say. Remember, somewhere up the transit path there is always peering. So if you are buying from someone and you're not peering, somewhere up that path, that provider or the upstream of that provider, at the end of at the top of the chain, they are peering. So up the transit path, there is always peering, so why you want to use that peering and not promote peering at your levels? If you have a relatively smaller network, go and do more and more peerings, and it makes perfect sense to exchange traffic locally. More peerings means more entry and exit points in the backbone, so networks with high amount of adjacencies give a tremendous advantage that you have lots and lots of entry and exit points with the backbone. IPv6 deployment globally needs to accelerate, and remember, each announcement here carries a considerable amount of prefix. So each of the announcement is carrying lots and lots of address space at least, and some of the considerations, as I already said, there can be, and there are actually large networks which are well connected, say larger content networks which are not reflected in this data. If them or the other side, that is the other networks connected to them, start dumping data, we would see those, and one can have a better analysis of those, how they're connected. Announcements smaller than /24 and 48 are ignored, and we just looked into the adjacency. We did not differentiate it between peers upstream and downstream, because if you try to do that, you can do that for limited sets of players. You cannot do that at the scale of internet. It's tricky to find who is the downstream and who is the upstream if you ignore the announcements going towards larger transit-free or tier 1 networks. So that's about it. Thank you.
Yeah, thank you very much. Do we have questions or comments? So, okay, I have one until somebody goes to the mic. But can you also expand a little bit about what the impact of not having those many adjacencies for our networks in this part of the world and the internet here, how does that affect maybe even the end user, not just necessarily just the networks?
Sure, so I can make in multiple locations, including US, Singapore, Hong Kong, and lots and lots of POPs in Europe. And on one fine day, one of their interconnections with another larger providers in Palo Alto broke off. And as soon as that went off, they were routing traffic to that provider all the way from Singapore. And so if you have extremely limited paths, extremely limited peering, you end up in having extremely horrible routing. For most horrible, and even if it's not horrible in regular times, it would be extremely horrible if one of your peerings or one of your path goes down. So it's extremely important in terms of resiliency in the network. So when you're offering really high capacities, you want to make sure that traffic stays local. Traffic from within that region is not really getting routed from outside with terribly high latency and much larger bottlenecks.
Okay. If you have a question, please go to the mic. There are mics back there for questions. By the time you get there, I'll ask a very quick other question, which is, we've seen in this part of the world, it's changing, and it's changing quickly. Like Paul was mentioning, we're seeing more and more enterprise and banks and governmental ASNs popping up. But for a long time, the mentality was the one that would actually get an ASN and manage his own resources would be the ISP, and then the customers would buy from them. In this part of the world, at least, like I said, it's changing. But can you also expand a little bit about how that would impact the local internet here versus, let's say, other countries, let's say UK, where we see, you know, hundreds of ASNs in the country versus maybe a country that we only see 4 or 5 or 6?
Sure. So the fact that it should be the ISP doing peering for you, and you must be connected to your ISP, it goes back in the case when a lot of people used to say that internet comes from US, right? Now, as the content has spread out and lots of content is coming from CDNs and limited sets of networks which have global presence, it makes a lot more sense to have peering, and one can offload a considerable amount of traffic. Most of larger networks, say you took the example of UK, they told me, so in terms of the eyeball players, they can offload as much as 70 to 80% of their traffic, and this is really high. So for remaining 20%, they can go with transit. For 70 to 80%, they are relying on peering with direct interconnection, and extremely likely with a member which is on the same layer 2 fabric. So extremely low latency, extremely high performance.
Okay, yeah, the question? Please just name an affiliation.
Hi, my name is Maher Qasim. I'm from Masco Group Dataport Links Lebanon. We're an ISP. You had some very interesting data, and I was wondering if you could provide us with maybe a central source to collect data such as that, and maybe data for traffic to and from AS numbers, your AS number, our AS number, anybody's AS number, and the type of traffic.
Sorry, if I understood correctly, you are asking for any source which can provide you this data?
Yes.
So we will probably publish this data. The challenge is there are lots and lots of ASNs, so probably I might end up in writing a tool where you can put your ASN and it just shows your peering over time. You might have seen our tool bgp.he.net, which gives the latest state, which is updated every 24 hours. We do not publish historical data in that tool as yet. The tool has limited historical data with respect to how many adjacencies were there over last few months, but we are not really collecting and keeping the data for like last 10 years or so. So for this specific data set, I can probably publish it online and share it over there.
Yeah.
So happy to see the first question, the Lebanese. Thank you for coming up and asking.
I also think Kaveh wants to comment on this as well.
Yes, thanks for the presentation. Comment to Maher.
Name and affiliation, sorry.
Sorry, cover arrangement RIPE NCC. So another source is RIPE stat. So if you go to stat.ripe.net and enter any ASN country code or prefix, you can actually get all kind of historical data also, like, and we have many visualization tools like BGPlay, where you can go back up to, I think, 1999. So in December 1999, we have routing data basically per 5-minute intervals till today. So the RIS project is the one providing data for that. So try stat.ripe.net. That will give you a lot of information. And if you're running an IXP in the region, we would be more than happy to work with you to install a RIS collector box. So your data directly from your IXP goes back to the RIPE backend. A question about IXPs, which is a bit, because I also really promote IXPs and I like to see more of them in the region. One of the requirements, especially highlighted here, is all over the world, but here is much more visible, and sometimes that stops IXPs to being formed, is LI, lawful interception, or LEA requirements, and especially in this region. And I was talking to a few people who have operating IXPs in the region, and this is one of their questions as well. So do you have any solutions or any ideas how IXPs can work with LEAs, basically to be able to provide lawful interception interfaces or things like that? Because this is one of the reasons in Middle East we don't see that many IXPs.
Sure. So I I'm not really familiar with the policies over here in this region, but since I come from India, we see similar requirements or for part. And this is more tricky. I don't really have a solution, but I can explain it gets trickier, especially with the fact that IX peering is pretty much layer 2. So you cannot really expect internet exchanges to be keeping some kind of logs or dumping some kind of data. So it gets very trickier. Maybe it makes more sense to consider the fact that at the end of the day, it's the ISPs which are providing the services. Anyone who has the services comes via an ISP, whether it's a layer 1 circuit or a layer 3 transit. And those are regulated, and those have those mostly the lawful interception part. So maybe one should think about not really putting the limb part. That's what, again, my personal opinion, into the exchange, because as long as that is covered on the ISP side, why you want to have the limb on the multiple side of the links? And furthermore, even if you do, then how would you technically do it at just a layer 2 switch, which is just exchanging traffic? You would end up in maybe having a layer 3 exchange, which would be horrible. We don't see any larger exchanges which are running layer 3. Maybe just few providers selling IP transit, partial IP transit in the form of layer 3 exchange.
Thank you.
Thank you.
Yeah, so I'll just echo one thing that was mentioned, that we do need to host a lot more of these collectors in this part of the world, whether they are the PCH collectors, whether they're the REIS collectors from the NCC, whether they're the University of Oregon Route View collectors, because it gives a better measurement for people doing the research like this, and for others that we're going to be hearing from later this day on how the internet is actually growing in this part of the world, and it gives us gives a better perspective for those that are actually interested in coming in this part of the world and doing business here to see how resilient the internet is.
And I would like to say, so many of these collectors are based on multi-hop sessions as well. So in case of PCH, it's the local device, AS3856 collecting the route. So Nishal is here. If you're interested, maybe you can speak to him. For Oregon route views, it's just a multi-hop session from your router where you exchange your routes. And since you exchange your full table, that gives a visibility to the entire internet on how your interconnections has been. And that if you have lots of peering, you'll end up in top ranks in most of these data if that data is visible outside.
Yeah. On that note, thank you very much. Please join in thanking the speaker.